Can you hear me? All right. So hi everyone. Thank you for having us here. A few things about me. My name is Dimitrios Valsamaras, and I'm engaged in computer security since 2002. The last couple of years, I focused on Android security, and a few months ago, as I said before, I joined the Microsoft Defender team as a senior security engineer. And with me,
my name is Shin Jung. I'm also a senior security researcher in the same Microsoft Defender research team.
And we're here to talk about how an Android application can drain your wallet. And the reason that we choose this category is due to the fact that it has a very interesting and very unique flow from a researcher's point of view. Besides that, there are thousands of posts out there about this kind of malware, but you will rarely find something which talks about how this malware actually works. So before I start, let me start with some definitions that we are going to use in the next slides. And first of all, what is billing fraud? So with billing fraud, we refer to the code which charges the user in an intentionally deceptive way. Oops. What do we have here? OK, all right. And we have a couple of subcategories of billing fraud. We have SMS fraud, we have call fraud, and we have toll fraud, with the last one being the most interesting and the one that we're going to focus in this presentation. So when it comes to toll fraud, we're talking about a malware category which has billions of dollars of revenue, yearly revenue, and it is one of the most prevalent PHA categories according to the Google Play Transparency Report. Additionally, it's a malware category which is very popular since it has the Google Play Store as the main distribution mean. And this back since 2017, when we found one of the largest toll fraud categories, which was actually the Joker. Now, what is the WAP billing mechanism? So the WAP billing mechanism is a billing mechanism actually, which uses a wireless application protocol in order to enable the user to purchase products and services online and get charged directly to their phone bill. Now here, if you see on the right side, I have the requirements of such a subscription. So first of all, customers of a specific, let's say, SIM operator are only eligible to be subscribed for a specific service. Then the customer, in order to subscribe, it has to navigate to a specific website. Then the customer will receive an SMS, which will inform about the billing interval, the next billing date, and these kind of things. And finally, the customer cannot be subscribed more than one time to a particular service. Now, take a note of the last one, because we're going to use it in the next slides to see how this is bypassed from malware. Now, let me summarize the steps so we have a good overview of what is going on. So first of all, the user will navigate to the WAP-enabled website. The server will send back the subscription page. The user will click on the subscribe button. The server will receive the request, send an OTP, a code, which can be sent actually using SMS or even the USSD protocol or even HTTP. Then the user has to submit this back to the server. It's going to be verified by the server. And finally, as a last step, the user is going to receive the SMS that we said before, which has this type of information. All right, now this is the normal, let's say, flow of a WAP billing mechanism. Let's see what is a fraudulent subscription. So fraudulent subscription is a type of subscription which takes place without the user consent, without the user interaction, and actually without even being noticeable to the user. So the malware has to take a series of steps in order to do that. So first of all, we said that the user has to be on a mobile network, so it has somehow to wait for the user to switch to a mobile network or force the device to switch to a mobile network. Then it has to navigate to the subscription web page, emulate actually the user click on the subscription button, intercept the OTP, which is sent from the server, send it back on the server, and finally keep all this process silent because the user has to be, all the process has to be not noticeable to the user. Now, first of all, before everything starts, one thing that has to be sure is that the SIM operator which the device is registered to is, let's say, it belongs to the target list of the malware. And this happens due to the fact that specific payloads target specific SIM operators. And this, again, is due to the fact that each SIM operator has a very unique flow when it comes to the subscription process. So in order to get this information from the device, they use either the MCC or MNC codes, which can be fetched from the device using these API calls there. So either the get SIM operator of the telephony manager class, or the get method of the system properties class. Now, the difference between these two is that the first can be simply invoked by importing the class, the telephony manager class, while the second one is marked as a system API and has to be loaded using Java reflection. Now, here on the lower side, you see an actual code of one of the latest Joker payloads, which checks about what I said before. If the SIM operator starts with 655, which is actually South Africa SIM operator, it will proceed to do the next steps. Now, first thing, the device has to be on a mobile network. So either observe, wait for the device to switch to a mobile network, the user to switch to a mobile network, or force the device to switch to a mobile network. So before SDK 29, we had this type of technique. So use the connectivity manager and get a network info object, and from there, extract, find the type of the network on which the device is subscribed to. The other way is using the set Wi-Fi enable of the Wi-Fi manager. So you can use the specific function in order to disable the Wi-Fi of the device, and the device will switch to a mobile network. And this, again, was before SDK 29, because on SDK 29, this was deprecated. Now, what we saw on the latest ones is the following. So create a network using the network request builder. So this is actually to define some specific capabilities. Then request this network from the connectivity manager. And finally, when this network is available, bind the process to the network. So again, on the right side, you can say exactly that. So create this network, request specific capabilities. So to have actual internet connectivity and the transport to be through a mobile. Use the network manager, the connectivity manager, in order to request this network. And finally, when it's available, bind the process to the network. All right. So assuming now that we are on a mobile network, what is the next step? The next step is to get offers, to get, let's say, the web pages on which the malware has to navigate in order to subscribe. And this, of course, is happening with, by communicating with a command and control server. So it will communicate with the command and control server, and we receive back an array of offers. So these offers, between else, they have URLs, which actually the malware will navigate, and they will route it through a redirection chain, which finally will end up to the landing page. So we see something similar there. So this landing page actually is going to be loaded in a web view, which is not visible, of course, to the user. The user, again, doesn't say anything. A very important component which is used by the malware is the Android OS handler. And what this handler is doing is waits, listens for signals for, which correspond to key stages of the process. So imagine that when the page is loaded, the malware will send a signal to the handler, or when SMS is received, it will send in, again a signal to the handler. Now the handler will act according to the ID of the specific message. It will take some kind of an action. Again, this is from the last Joker payload, which shows exactly this technique. So get the message, and depending on the what parameter of this message, acts accordingly. So, as I said, one key state of the subscription process is when the subscription page is loaded. So now the malware has to take action in order to emulate the click on the subscription button. And how it's done that? It does that. So one of the most common techniques that we saw is by using JavaScript, injecting JavaScript code. So what this code will do, again, this is actual code from which was fetched from malware. So it will scrap the page and search for elements which are semantically relevant to the subscription process. For example, they're tagged like confirm, subscribe, etc. And then it will send these elements to the function C here. Now, what this function C will do, remember I told you to take a note that the user cannot subscribe to more than one time to a particular service. So how the malware has to make sure that the page has not been visited in the past and has not been clicked in the past. So first of all, it will call the JDH function there, which will check for a specific cookie. So if this cookie has been set, it will return false. Or if it's not there, the cookie is not there, it will just set the cookie and return true. Upon returning true, the function will simply submit or click the element which has been set as a parameter to the specific function. So this is how it tracks the visiting on the specific pages and how it emulates the clicks. Now, another thing, we said that the SIM operator will send an SMS in order to verify the subscription process. So this is done usually using an SMS, like I said before. So the malware has to intercept the SMS communication of the device. And how this is done? So either using an SMS broadcast receiver, this is the most, let's say, easy way, or bind the notification listener service, or finally using an SMS content observer. So let's see each one of them. Now, using a broadcast receiver, make sure, first of all, that we have the required permissions, which is actually, in our case, is receive SMS. The others are for the other steps. And send SMS because they have to send the SMS back to the server. So register broadcast receiver, and in the on-receive callback, examine the message, the body of the message, search for specific keywords. If this keyword matches, then extract the OTP, and of course, send it back to the server, using, for example, the send text message API call. Another way is using the notification listener service. So create a class which extends the notification listener service. Again, the logic is the same. What differs is the implementation. So hook the notification posted. When notification is posted in the device, this is the function actually which is called. So this is the callback on the notification posted. And again, it will search the body of the notification to search for specific keywords. So if this keyword is there, it will extract the message and again, send the OTP to the server. Another way, a little bit less often, that we notice is by using a content observer. So what a content observer does is receiving callbacks when a change to a specific content has happened. In our case, what malware care most is about the SMS inbox. So when a change happens there, it will simply, the on-change callback will be triggered. And again, the same process. It will check the message, it will check the body. If there is a specific keyword, it will extract this keyword and send the OTP to the server. Finally, as I said, all this process has to be silent. The user doesn't have to know about anything. So all the notifications have to be suppressed. Now, since SDK 18, one application which has the notification is allowed it actually to bind the notification listener service can cancel notifications which are sent from other apps. And this is done by using the cancel all notifications function or cancel one notification with a specific key or a set of notifications using an array of keys. So the other way, of course, is using the abort broadcast, again, on the on-receive callback of the broadcast receiver. So let's summarize what we have so far. So we explain what is the WAP billing mechanism and how it can be used to enable the user to purchase some products or services online. Then we show the steps which are required for the user in order to be subscribed to a service. And then we show how these families actually are simulating the steps in order to achieve this type of subscriptions. So navigate to the WAP page, simulate the user clicks, intercept the OTP that probably is sent from the server, and suppress all this type of notifications that we said before, all these things that we showed. Now, you might wonder that, okay, we have a malware which has a lot of API calls, which has a very complex, let's say, behavior. It has a lot of permissions, so that can't be that hard to detect. how it explains the fact actually that this one is one of the most shown categories in Google Play. So I handle the thing back to Shang. Okay.
So, so far we have talked about and we have shown about some details of toll fraud actions, and that we have analyzed in the last payload of the malware, and focus more on those toll fraud techniques. Now, let me just pause here a little bit and then question ourselves to ask questions like what challenges do we have in analysis, and what makes detection harder, and what can we leverage for design for detections. In the following slide, we're gonna first talk about the detailed techniques that used before toll fraud actions, and those techniques basically are try to prevent us from analyzing and then detecting this malware. Later in the slide, we are also going to show how we can leverage heuristics for detections, which we can have on client and the cloud. And at the end, we can you're going to have ideas about why detection of this type of malware is hard, and what heuristics and detection mechanisms we can use it for make it better detections at the end. So first, for the detailed techniques, this malware uses multiple stages, which means the malware moves on over from one payload to another payload multiple times. At the same time, the malware places clocking techniques. So that clocking techniques are basically to makes it evade itself from the analysis and detections. At the same time, the clocking techniques are to make sure if any necessary conditions by the malware are met before it moves to any malicious behaviors. So if there is a condition is not met, then there's no more any other further malicious action happens at all. So with the malware, we have analyzed it. It has 4 stages, and each stage moves on to another stage with dynamic code loading and clocking techniques. For example, this malware sample starts with a very simple messenger-themed application. And however, this malware decrypts an SF file when it starts the application, and then load the decrypted file with a system load for dynamic code loading in this first stage. And then the malware does a similar transition for stage 2 and then stage 3, but with a different payload in each stage. At the end of stage 3, it loads the last payload, which is for the toll fraud we have explained in the previous slide. But at the beginning of the last payload, it checks if the mobile country code is actually 6055. If not, there is no toll fraud action happens. As a reminder, we have explained the previous slide. So in the following slide, we are going to show each stage and then some clocking techniques and belongs to the stage. So in first stage 1, for example, as one of clocking techniques, the malware checks if the malware itself is in the Google Play Store. So if not, this just returning the false, and then there's no further malicious action happens. This clocking technique also malware itself to verify this malware is published by the Google Play Store as well. And when the malware passes the first clocking technique, the malware first look for the assets file. The file name ends with a 355. And then it passes to decrypt function, which is this one. And then with the input file path, and then the password string, and the output file path. So this malware picks up this particular file in the asset directory just because it wants to target a specific group of users out of in the same, I'm sorry. In the same the assets directory, there's a same file name prefixes with different numbers, but the malware picks up this particular file to target a specific group of users. And when in the decrypt function, which is this, and it uses the password string, which is passed in the second parameter of this function with the AES secret key spec, and decrypts the input file and drops it off to the output file path and in the cache directory. And then the malware loads the file, which is an L file format, and then loads with the system load for the dynamic code loading. And then when it loaded, then the malware just called it a native function, which called the coroutine exception handler that handle task. And then when it calls the native function, it passes its context and its asset handler, and then the same the password string, which is used to here as well. Then now we moved into the stage 2, which has the same context, but it runs in the native code. So we moved from Java to the native. Now, when the native function is called, this native function first looks for another asset file, which is the file name ending with the 300 at this time. And then this particular file is also picked up because they want to have a transition to make it or the picks up the specific group of users out of the large set of users, and then drops off the file to the file B, and then this file B is XORed with a password string passed it in the last parameter of the native function. And then this native function, this XOR operation is basically turns the file B encrypted to the file L decrypted. So now we have a file L is in the cache directory. Then the rest of in the same the native function, it has some obfuscated encrypted strings, which in purpose for JNI function calls. So for example, one encoded string with one key is passed to the encrypt function in the same native code. It turns out to be a Delvik system DEX class loader. There are other encoded strings happens with a key and passed to the encrypt function, and then it has same the plain text decrypted strings. All those decrypted strings are basically used for all those decrypted strings are class names and then method names and parameter signatures that are used for the JNI function calls. For example, here we have a find class and call object method and call static void method. These all JNI function calls are for the malware to loaded the class com.add view of the last payload, of the next payload, and invoke the function pulse-in of the class. So eventually it calls the com.asView the pulse-in method at the end of this call static void method. So now we move into stage 3, which has the same context as the previous stages, but it gets back to the Java code now. When this class, which is a com.addView, is called, and then it's a method pulse-in is called. There are at the beginning of this class has some hard-coded strings, which are actually for Java reflection, and then the C2 URLs. And when this pulse-in method is called, it just calls another method, which is a get star. And then this get star method basically try to make it the HTTP connection to download the next payload. And then when we download it downloads the XN30 file and drops it off to the text file name NVI. So after it downloads it, it just basically calls another the method, which is a star SDK. And this time, this star SDK does the same thing for the loading and the invoking the method for the next payload, which is com.xn30, and then the com.xo30's xn30 method. But this time, it uses a Java reflection instead of just calling the DEX class directly. So this stage 4, which includes this com.xn30 class, is actually the starting point of all the fraudulent subscription process of toll fraud actions, which we have been explained in the previous slide by Dimitrios. Now, before we move we get into the detection, let me introduce summarize the view of all the techniques in MITRE's mobile matrix used by this malware. And for example, we have talked about the download the new code at runtime, capture SMS messages, and alternate network mediums, and input injection, and SMS controls, which are all used by the malware for this type of toll fraud actions. And we are going to use this MITRE mobile techniques to improve our detection design later. And then at the same time, we're going to introduce some of our heuristics for the detection we can leverage on the client and cloud. So as a perspective of characters of those techniques, which consist of initial access and detection evasion and exploitation. These can be a penetration strategy. So when we see initial access, especially, for example, the technique called deliver malicious app via authorized app store, which is a Google Play Store, for example. It was quite interesting to see how this type of malware gets into the Google Play Store. For example, the malware we analyze it starts from very benign features, but it has a very popular category of the app. just like a messenger or theme. You provide the themes. So when the malware gets popular, let's say more than 10 million installs to the user in Google Play Store, then they get updated themselves with malicious behaviors. Those malicious behaviors comes with payloads as obfuscated or non-obfuscated. They get from local SS directory or dynamically downloaded from the C2 server. So when you think about detection against the penetration test, penetration strategy, we can the penetration strategies can be narrowed down with some heuristics. So when we say heuristics, it can have different the properties we can get from multiple sources, and then such heuristics to get those information can be less granular, so we can get from the Google Play Store informations. So when we use a less granular information of application, this allows include more similar types of suspicious applications. So which we called it as the secondary characteristic. So we mentioned this secondary characteristic first before we mentioned the primary characteristic, because we think in our detection design, the secondary characteristic can come first to filter and then making the largest set of similar apps, similar suspicious apps. So in the secondary characteristic, we are very interested in application with excessive permissions and common or consistent user interfaces in icons and some policies, or the similar package names, even the suspicious developer profile in names and emails, and user complaints. At the bottom of the slide, these are such applications and their names. We could have collected through in the Google Play Store as an example of a suspicious applications. So now we can have a large set of the suspicious application that we want to look for further with our primary characteristics. So the primary characteristic, when we narrow down the large set, this can be specific instead of a general. So we identify the API calls and the required permissions which the TOEFL malware or this type of malware normally performs. So in the primary characteristics, we have two groups of API calls, one for detection evasion, the other for fraudulent subscription. In detection evasion, is mostly try to use it for dynamic code loading with the DEX class loader or in-memory class loader, or sometimes they use a JavaScript injection with an add JavaScript interface. And then in fraudulent subscription, there's a telephony managers get SIM operator, which is pretty critical in our investigation. Then there's a connectivity managers get active network info, and Wi-Fi managers set Wi-Fi enable. There is also the SMS managers send text messages. These are the pretty interesting API calls we wanted to look for further for the TOEFL malwares. There are other API calls we are also in the table. Now I'm going to hand over to Dimitrios to show the client and cloud side of detections.
Thank you. Okay. So, now I guess you have an idea of what is the challenging thing here. So, actually, you don't have the code, which is actually the malicious code. Either it's downloaded, or either it's encrypted, or either there's some kind of steganography process which extracts the malicious code, loads it somehow. And now that you have a full overview of what's going on, let's see what chances do we have in order to detect this type of malware. And starting from the client side, I will be honest with you, we don't have many chances there because the operating system, the Android operating system, imposes serious restrictions on what one application can fetch for another application, as you probably know. So each app is trapped in its own sandbox, and the information that can fetch for another app is controlled by the operating system itself. So not much that we can do at this point, besides some traditional static scanning, which again is based on information which is going to be fetched from the cloud. Another thing that we can do, of course, is maintain a blacklist with command and control servers, observe the HTTP communication, and if we see some kind of a malicious activity, then, yeah, trigger some kind of an alarm in order to alert the user or even do some kind of an action. Now, when it comes to the cloud side, though, the options that we have there is quite more, right? So first of all, we're talking about a pool of samples which has a feed, a steady feed, which might be either from the Play Store or either off-market. So what we suggest here, what we propose here, is a multi-stage process which has as an objective to have the best results and at the same time use as less resources as we can. So during the first phase, what we do is actually to scan for secondary characteristics like the ones that Sang sent before. So developer names, similar icons, names of the function. These are all automated generated because they're part of their upload strategy in order to publish something, stay in the Google Play as much as possible and infect as many as possible. So they have similar characteristics. And these are the secondary characteristics that we are talking about. Now, the outcome of this process, of this step, is either the app can be suspicious, so it gathers some of these characteristics, or it's not suspicious at all, so it can be skipped, or finally, it has a specific threshold which requires the app to go to the next phase. So the next phase is again static scanning, which based on either known API calls, known permissions, or either code snippets that we fetched from other already known malware. Again, the outcome will be the same, either suspicious or can be skipped. The application might not have, for example, one significant permission which is needed in order to do this kind of stuff. And then the last one and the most, let's say, resource consuming step, which is the dynamic analysis, of course. Now, the problem here is try to trigger as much as code as you can, right? So you have to interact with the malware in a clever way in order to trigger some kind of a malicious behavior, and at the same time you have to observe the HTTP communication, what kind of information is exchanged with the server, use some kind of binary instrumentation, for example, log the API calls, or even change, modify what values are returned from these specific API calls that we talked before. Again, we're trying to trigger some kind of a malicious behavior, right? That's what we're trying to do right now. Then dump the memory, because search for some DEX files, that these DEX files might be loaded using dynamic code loading, or dropped somehow, or in memory class loading, or whatever. Any way of dynamic code loading will do here. Even this can be used to bypass some packers, of course. Another thing, observe the data directory of the app. If a file has been dropped there, which was not in the initial APK, something is wrong, something might be unknown or something, so it can be decrypted, can be loaded. Another thing, trace, of course, the JNI calls, how it communicates with the native layer, and dump the memory, of course, of the loaded native libraries. the final outcome of all this process is, of course, to create signatures. The traditional well-known signatures, which are going to scan for specific code patterns and enrich our database in order to be able for us to get this type of samples in a lower, let's say, level and try to avoid this resource-consuming last few steps, right? There are a lot of things that can happen on the prevention side. Sang, you want to finish?
Yeah. So as an additional note for prevention, the Google also updated their Google Play Store policy. So to address the problems with permission, which are mostly high risk and sensitive permissions. So when the developer completes the form of permission declaration, then they will just restrict access to the sensitive sensitive user or device, or they allow them in the action. This happens in November of 2021. For another, the problem we have seen during this analysis was binding notification listener service, which has been used to get the message from the incoming messenger or SMS. So we have initiated the conversation with Google security team to explore more mitigation cases against any malicious use cases they were using the binder notification listener service. For example, what we already mentioned in the previous slide. Okay, so thank you, Troopers, for providing the opportunity for us to present this talk, and thank you for attending this talk.